Good morning, ladies and gentlemen. This is Ben Keiser with Applied Flow Technology, and I want to thank all of you for joining us today. And we're very excited to present to you all as usual. We hope that everyone is staying safe and well and sane during this period of time that we are having, and hope that everyone is remaining healthy and AFT is doing well, and we are all able to work effectively from home. And so, thankfully, AFT is still business as normal. So, whenever you have questions or need tech support, you can call us and you'll be able to get a hold of us right away. A few noteworthy items that I want to mention is we just recently released AFT Fathom and AFT Arrow within the last couple of months. So if you have access to AFT Fathom, then you can download the latest version of AFT Fathom right here from our website, Fathom 11. And then AFT Arrow 8 was also recently released. You can download that here. I would highly recommend that you ensure to sign up for notifications. This way, whenever we come out with a new maintenance release or new version, you'll be emailed so that way you can get the link to download the latest release and get updated to it. Also, keep an eye on our newsletter under About and then News, because very soon we're going to be releasing AFT Impulse 8 really shortly. And for the Impulse users, you'll be able to download that right here on the AFT Impulse page. So stay tuned for that announcement. It'll be happening here within the next couple of months that we're planning here. All right. Today we have a very special webinar because Applied Flow Technology has a sister company called Purple Mountain Technology Group, which offers consulting services, and they are experts on flow analysis. And so today, the project manager of Purple Mountain Technology Group, Mr. Dylan Witte, is here to be able to present for you all, and we're excited to be able to have him teaming up with us on this. And so, in order to get more information about how Purple Mountain Technology Group can help you, their website is www.pmtechgroup.com. Again, that's pmtechgroup.com, and you'll be able to learn about the various services that they offer. You could read about the vast area of experience and projects that they've worked on. And then ultimately, when you want to be able to contact them for their services and get a hold of Dylan, you can simply click on the contact button. And this is where you can find the information for contacting the Purple Mountain Technology Group, and they'll be able to help you with your flow analysis. So with that, I'm going to go ahead and kick things over to Mr. Dylan Witte, and he will take it from there. And so, Dylan, we are excited to see what you have for us today.
Great, thanks for the good introduction, Ben. We're attached at the hip to AFT and enjoy working with them. And we do tons of different consulting projects. One of our main things is waterhammer and transient analysis. That's kind of our bread and butter. So if you ever have any questions about that, be sure to reach out. That's why a lot of the webinars that I've been doing with AFT have been kind of focusing on impulse. That's one of my favorite areas to work in. And today we're going to kind of narrow down our focus into a specific fluid property that is really important for waterhammer analysis, but isn't really used many other places for like normal steady state analysis, but it is one of the more important things to know, and it's one of the harder things to find out. So we're going to talk about that. And like Ben said, I'm project manager for Purple Mountain, and all of my info is there. So if you want to shoot me an email or give me a call, all of my info's down here in the corner. I'm going to try to be cool like Ben and use my drawing tools. Let's see. So yeah, there's my info down there in the corner. And let's go on to the next, let's see, base hull drawings. And let's go back to normal non-drawing mode. Okay, so introduction. Essentially, all fluid properties are kind of the starting point of any flow analysis. If you make any mistake with the viscosity or the density, those errors are usually pretty obvious really quick. If you accidentally put a like a density in pounds mass per foot cubed as defined by a specific gravity, that becomes obvious really quick. But any mistake here kind of propagates throughout the whole system. So you need to make sure you get these right. And then they're difficult to come by. And one of the things we're going to talk about today is water, even though it's the most common fluid in the world, and it's the most common pumped fluid in the world, it's going to behave differently than you expect it to oftentimes, depending on the system, depending on where it's coming from, and depending on its air content. That's the huge thing for waterhammer analysis, is sometimes there's entrained gases in the water, so we have to be cognizant of that. And when we're talking about liquids, anytime you take your fluids class 101, one of the first assumptions is fluids density doesn't change with pressure. Well, I mean liquids, and that assumption starts to break down when you're looking at transient flows. So all liquids are slightly compressible. They're far, far, far less compressible than gases, but these liquids do change density with pressure slightly, and that's one of the main reasons we see pressure waves. So when we're talking about steady state, the real reason we do that is it makes solving the Bernoulli equation to find pressure drop in a pipe pretty much easier using a constant density and for mass conservation. And that's what Fathom does. And it's one of the most basic assumptions. And it works really well for if you're doing like a pump analysis to try to size your pumps or things like that. But once you start looking at transients, it doesn't work quite as well. So when we're talking about transient analysis with something like AFT impulse, it's no longer valid. So the steady state is perturbed by things like valve closures, pump trips, other things that can happen in the system, ruptures. But the most common things we end up looking at in impulse are valve changes and pump changes. So in order to do that analysis properly, you have to know how waves travel through the piping system and be able to determine the magnitude of the associated pressure changes. So in order to do that, we need more information about the fluid. And that's specifically how the fluid density responds to pressure changes. That property in your fluid properties window is called bulk modulus. Okay, so the definition for bulk modulus is essentially it's K equals rho times dP over d rho, where K is bulk modulus, P is pressure, and rho is density. So that's the equation of it. So you can kind of see if you actually divide both sides by dP, you can see that any associated change with density has a kind of corresponding change in pressure, and that K value of bulk modulus helps scale that. So that's why the units for K are pressure units, whether that's PSI or megapascals or gigapascals. That's why that unit is in pressure units. Okay. So one of the things we can find if we know bulk modulus of a fluid is an acoustic velocity. So this acoustic velocity is shown in that equation, square root of K over rho. So, but that's in a unbounded fluid. So that's like a wave in a pool or the ocean. So there's no really mechanism to bound the wave motion. Or essentially in a completely rigid pipe. So this is kind of potentially worst case scenario where you have the fastest acoustic velocity or wave speed. So what we're going to talk about is wave speed. Again, I always talk about wave speed a lot in my webinars, but wave speed is king. And in piping systems, not just liquid pools, some of the energy in a pressure wave distorts the pipe itself. And that distortion of the pipe reduces the acoustic velocity. So that reduced velocity is commonly referred to wave speed or sometimes celerity. And the wave speed is critically important because it determines things like pipeline period or communication time. So, and that's equal to 2L over A. So where 2 times the length of your piping system divided by the wave speed. And one of the more common assumptions or things that's pretty important is if you have an event occur in a faster time than this 2L over A, it's considered an effectively instantaneous event, and you're going to see potentially the maximum pressurizer in that event. That's a common assumption, and it's typically overall true, but there are exceptions, and looking at things as a system and how waves respond and how equipment responds can change that. And then also critical things can occur like column separation or line pack that can actually change what your maximum pressure you're expecting to see could be. And it also, wave speed also determines how your pressure responses to a corresponding velocity change. And they have a dramatic effect on the analysis. And so when we're looking at calculating wave speed, this equation on the right takes into account bulk modulus, your K, your density, other things like a pipe constraint coefficient, which determines on essentially how your pipe is supported. And then you get your bulk modulus again, your pipe's properties. That's critically important, remembering your pipe's properties and diameter and thicknesses. Oftentimes people will assume maybe just ANSI steel, but if you have something like PVC, your wave speed's actually going to be a lot lower in something like PVC because it's going to distort more than something like carbon steel. So that has the effect of slowing down the wave, and your results of your analysis are going to be far different. So typical wave speeds for water and steel piping are anywhere between like 3,000 to 4,000 feet per second. If you're looking at PVC, it's closer to 1,200 feet per second. So it's 3 to 4 times slower in PVC than in steel piping is fairly typical. But you can calculate that if you know the properties of the material. Okay, so using that equation is the most common way to determine wave speed for an analysis using AFT impulse. A lot of that's done automatically for you if you just put in the bulk modulus and your pipe's properties. You don't have to actually do that hand calculation in order to calculate wave speed. It's a good way to kind of determine wave speed if your system has varied pipe sizes, varied thicknesses, varied materials, etc. So that's great, but sometimes it's hard to come by this bulk modulus value. And that bulk modulus value can change with things like system operating pressure or temperature. Some fluids are really sensitive to temperature. And if you get closer to their vapor pressure, I mean, they're getting closer and closer to that vapor phase. And that means they're getting a little more compressible. So that bulk modulus value changes, sometimes quite dramatically with temperature. So, and it's especially true of hydrocarbons because oftentimes they're mixtures of complex things, and sometimes parts of the solution are more likely to vaporize or more sensitive to temperature than others, like the light hydrocarbons versus heavier hydrocarbons. So be aware of all of that as you're doing an analysis. Okay, so we're going to talk about hydrocarbons for a decent amount of time because that's typically what's the hardest thing to find. Things like water, you can find bulk modulus a little bit easier. It's a little more well studied. And hydrocarbons, the reason they're so complex is each mixture, each exact composition is a little different from place to place depending on where they're extracted from. And their properties are highly temperature and pressure sensitive. That being said, there are some common assumptions and common rules of thumb in order to get these properties that you need based on various pressures, densities, and that was supposed to say temperatures, so I accidentally wrote pressure twice. So we're talking about pipeline rules of thumb. What better book than to use besides pipeline rules of thumb? So my reference for a lot of this is this 4th edition by McAllister. So there's a couple really good references in there that I use a lot for my analysis. And I don't have a copy of these API manuals, but these are the chapters from API where these comes from. And there's a formula in there called this ARCO formula, which actually works pretty dang well. So if you need to find your adiabatic bulk modulus, all you need is your average pressure in the line, API gravity, which is sometimes hard to figure out. Sometimes you know it, sometimes you don't, but you can calculate that from your specific gravity, and a temperature. An important thing for lots of thermo analysis and lots of equations is this is an absolute temperature with degrees in ranking. So don't use Fahrenheit for that. You're going to have to add about 460 degrees in order to get an absolute temperature in degrees ranking. Okay, and then there's a graph here that works pretty well from pipeline rules of thumb that allows you to get your bulk modulus for various API gravity crudes. And that ARCO formula is also pretty much only applicable for crude oils. So this works really well between 20 and 65 API. And it only shows for 60 and 80 degrees. So it's kind of limited, but that's kind of typical ambient operating pressures. Sometimes you'll be at a higher temperature. And at a higher temperature, your bulk modulus is going to go down. So typically when I use this, I actually use the 60 degrees Fahrenheit graph, as it's going to give me a higher bulk modulus, which is typically more conservative because it's going to result in a higher wave speed. And a higher wave speed is going to give me a more severe pressure response in almost every situation. So looking at that is typically how I go about it when I'm looking at a crude oil analysis. And then here's just a quick useful conversion in case you don't know how to calculate from API to specific gravity. That's just kind of there for reference, so you can use that real quick to go back and forth between the two because you need API gravity to use those equations, but you have to put your density into impulse in specific gravity or kind of a actual density unit as pounds mass per foot cubed or kilograms per meter cubed, something like that. Okay, and what I like to use is either the NIST REFPROP, which was recently added to Impulse in the last version, for known compositions. This is a typical condensate composition I got for an analysis a little bit ago. And what I want to show is actually using this composition in Impulse and how I use that to get my fluid properties. So if we actually open up Impulse here and go up to my system properties, I can actually create a new fluid using NIST REFPROP or the Chempact fluid. But for this example, we're going to use NIST. And I'm going to create a new mixture. I'll call it condensate. And we're going to find our first fraction. Ooh, I wanted to do that. I have to select mole fraction first. Down here, then create a new mixture. And it depends, you can do it by mass or molar. So be aware of that. That's not the same as volume fraction. So if you do have a volume fraction, you're going to have to convert that to either a mass basis or a molar basis for this to be accurate. And my first mixture composition was butane. So I can hit B, find butane. I had 0.5% of that. Next one was isopentane. And I had 16.5% of that. We can do pentane. And there was, let's see, 23.5. And then hexane. I had 24.5. Heptane. Accidentally, I think I accidentally hit the help button. Let's see, heptane's right there. Now we had 22.7. And then octane. Octane was our last one. And my molar fraction here keeps on updating, so it completes 100% molar fraction, so we don't have a missing percent or something, but 12.3% was my fraction of octane. So I'm going to add that, hit OK. So now I have this mixture, and I need to add my operating pressure. And then I was operating at an average of 190 psig, and my temperature. So it'll give me a valid temperature range for this mixture. And I'm within that because I'm operating at 125 degrees Fahrenheit. So if I calculate the properties, I can see my density, my viscosity, and my bulk modulus. So the bulk modulus for water is about 300,000 psia for average water. But in this case, I'm about, let's see, 1/5 of that, 1/6 of that at 64,000. 665 psia, so that's much lower, and that's because we're using a kind of a light hydrocarbon mix, so it's a lot more elastic than water is. So, and we can see how sensitive this is to temperature. So if I go closer to the upper regions of that, if I increase my temperature by 125 degrees, my bulk modulus goes down by about 30,000. So it is highly sensitive to temperature, so keep that in mind. You can see my density change and my viscosity change and all that. So, and even my vapor pressure went up a lot. So keep that in mind when you're looking at all of these, that yes, bulk modulus is sensitive to this, but so are all of your other properties. So when you're looking at a specific mixture, test it out a little bit, maybe do a sensitivity analysis using various temperatures. Okay, so let's go back to the PowerPoint. Okay, and some final additional concerns. Sometimes using that equation to calculate wave speed based off of bulk modulus and your pipe properties isn't valid anymore because of the assumptions that are built into that equation. So if there's high percentages of entrained air, it's oftentimes better to look up data from a reference and actually manually input a wave speed. Large amounts of entrained air are going to dramatically lower your wave speed because that gas in your fluid is essentially, it's compressible, and that changes how your fluid is going to behave in a transient analysis, or in a system, normal system, water system, things like that that have a lot of air in them. And Witte and Streeter has a good graph about that. So I'll have that reference at the end. If you have non-circular ducting, that equation we showed earlier is based off of circular pipe. So if you have rectangular duct or something like that, it will deform differently than circular pipe, and it has the effect of severely reducing your wave speed. Your pipe's also a lot less strong because of that shape, but that's why pretty much every single pipe is circular. If you have plastically deforming pipe, that will change how your wave responds. And if you have flexible hoses, so all of this is kind of for, if you think about how stiff your pipe is and how stiff your fluid is, that is what's determining your wave speed. So if anything is abnormal about that, or a little bit atypical from your standard above ground, well supported steel pipe, chances are the wave speed is going to be different than if you just look up what's wave speed for this fluid. You can't just use that value. You have to be aware of what is your fluid in. That matters a lot. So in those specific cases, you need to look up a reference to calculate and enter a user specified wave speed. One of my favorite books for transient analysis is called Fluid Transients and Pipeline Systems by A.R.D. Thorley. And he has a really exhaustive list of not only material properties, but ways of calculating wave speed in atypical arrangements. His list of what's wave speed in octagon pipe and things like that. So it's really interesting, and it's really useful to check out. So if you have questions about that, if you have an atypical arrangement, shoot me an email and I can talk to you about it and maybe help you find some of the properties you need in order to do your analysis properly. And here's kind of the references. If you want to look this up and buy it on Amazon yourself, I would highly recommend it. It's a really good reference, not only for looking up fluid properties, but just becoming a better transient analyst yourself. I use it a lot in order to find better things. And then there's always Witte and Streeter. That's always a great book. That's kind of the godfather of all transient analysis. So keep that in mind. And without further ado, I think that's it. I'll hand it back over to Ben. And thanks for your time, everybody.
Alrighty, thank you very much, Dylan. We greatly appreciate the presentation. That was excellent and some very useful knowledge that is imperative for doing flow analysis. So we really appreciate you sharing that with us. Okay, everyone, that basically covers it for today. And thank you all again for your time, and take care, be safe, and stay healthy. And we will see you all in the next webinar.
Hi, everybody.